First of all, what is combustion? Well, it's fairly straightforward in principle. You take a fuel, which can be anything of course, generally it contains carbon, and you mix it with oxygen at an elevated temperature. As soon as you get over an activation energy, then you drive a number of reactions. So for complete combustion of carbon, of course we produce carbon dioxide, and there's a delta H for this, 33.96 megajoules per kilogram. Incomplete combustion, which produces CO, there's a delta H much less, of course, 10.33. And finally, hydrogen in fuels, very energy rich. This is why hydrogen containing fuels such as methane have fairly high delta H's. So delta H for H2 plus a half O2 is 133.5 megajoules per kilogram. Oxygen in fuels doesn't contribute, it basically contributes just a little bit of oxygen. So if you're working at the stoichiometry of combustion, what you will do is you'll take your kilogram or your cubic meter of fuel, work out how much carbon is in there, how much oxygen, how much hydrogen. You'll sum up the amount of oxygen you need for complete combustion of the carbon, how much for complete combustion of the hydrogen. Then that will give you an oxygen requirement that you need to combust the fuel. You subtract the oxygen that's already in the fuel, and that will give you the stoichiometric amount of oxygen that you need to completely combust the fuel. Of course, oxygen is only about 23% of air, so once you know the oxygen requirement, you can calculate the amount of air that you will need to combust the fuel completely. And then when we have a certain amount of fuel, we've calculated the amount of oxygen that we need precisely. If you mix the fuel and the air in that ratio, that is called the stoichiometric amount of air that you need for combustion. Sometimes people call it the ideal combustion mixture. As it happens, fuel is hardly ever burnt in the ideal mixture for reasons that I'll explain to you. So basically, that's the reactions that you need. Forget about gasification, it's equally important, but not the topic here. Now let me take you back many, many years. The first year that you go into a chemistry laboratory or a science laboratory at the age of 11 in this country. And you go into a laboratory and the first thing you see is your chemistry teacher with a Bunsen burner in front of you. Bunsen burners are very good for driving reactions. And of course, you need to know the safety. And so what your chemistry teacher does is she lights the Bunsen burner, burning methane these days, of course. And you see this nice bright, luminous flame. And then what happens is your chemistry teacher opens up the little hole in the side of it to allow air to ingress in it, and the color of the flame gradually changes. So you have this nice, bright, luminous flame, and then gradually turns bluer. And if you were dealing with hydrogen, which you wouldn't be in a chemistry laboratory in the school, then the flame would be completely colorless, but you would certainly hear it. Now this is the simplest and you would think the easiest experiment of all. Unfortunately, this masks a whole bunch of very, very complicated chemistry indeed. And I'm going to argue that this underlies the problems that Volkswagen are having in trying to use fuels efficiently. Now let's start off with this nice, luminous, unstable flame. Unfortunately, I couldn't find a methane cylinder and a regulator, otherwise I would have brought up a little Bunsen burner. What's taking place in this flame is extremely complex. And it's a classic example of what's called a diffusion flame. And it is the least efficient way to burn fuel imaginable. So what's happening in our little Bunsen burner or our burner is, of course, we have methane coming up here, and we see this cone inside, and there's no combustion taking place here whatsoever. In fact, there's a little experiment you can do. You can take a little pipe, stick it into the middle of the flame, extract some gas, and then set fire to it, and you can have a little side flame. So here, there's absolutely no combustion taking place at all. Now, what is causing the yellowness of this flame is essentially incomplete combustion. What's taking place in the yellow part of the flame is that the methane is breaking down, the hydrogen is stripping off, the hydrogen is combusting, and essentially what you're doing is forming little particulates of soot. Soot is just nano-sized aggregates of carbon. And what is happening within the flame is that these small aggregates of carbon are glowing white hot, and this is giving you the coloration of the flame. So no combustion, partial combustion, and what is happening on the outside of the flame is that oxygen is diffusing into this. So you can't really see it from this picture, but around the outside you'll see a little blue corona, which is why I wanted to bring Bunsen burner along. And then we're getting complete combustion on the outside. So essentially, the chemistry that's taking place in this flame is governed by the diffusion rate of oxygen in from the air. And if you put your hand on top of this flame, which you can quite happily do for a few seconds, you'll note that it becomes black as you're getting soot deposited on your hand. So this tells you two things. First of all, a lot of the carbon is not being converted into CO2 according to our combustion reaction. So you're getting carbon deposited on your hand. And secondly, the very fact that you can stick your hand in the flame at all means that you've got a very low flame temperature. A few hundred degrees centigrade maximum. But the mean flame temperature is quite terrible. You can put your hand in and out of the flame. Probably not encouraged by chemistry teachers these days. But you can do it fairly easily, or you can, I guess, do it when the chemistry teacher's looking at somebody else who's trying to jump out the window or something like that. So this is a diffusion flame. It's incomplete combustion of the fuel. Low temperature, very visible, very low conversion. What's happening here, on the other hand, is much, much more efficient. What we're doing now is we're introducing some air or some oxygen at the bottom of the burner. Now this is not an optimized combustion chamber, it's just a little bit of tube with a hole in the side and perhaps a little diffuser around the outside. But what is happening is that now the air has time to mix, to pre-mix with the methane, so that when it comes out, we're not combusting just pure methane, which is coming from the center of our flame. Now we're combusting a not perfectly mixed, but a much better mix of methane and oxygen. And of course, we've got a lot of air there as well. So now you'll see there's no yellow coloration, which means that we're getting no soot formed in the flame, or if it is, it's getting converted into CO2 very quickly. So here we've got initial stages of combustion, and here we've got the hottest part of the flame. So we don't need much oxygen to diffuse into the flame. So this is kind of pre-mixed beforehand. So this is much, much more efficient. So, which is why we get no yellow coloration. We do get a bit of blue coloration because of the carbon present. And as I said, if this was a hydrogen flame, it would be completely colorless and therefore much more dangerous and incidentally much hotter. Now, the one thing you would never attempt to do with this is put your hand above it or through it. The flame temperature is very, very much higher. Now we're going up to peak temperatures, perhaps not in a Bunsen burner, but if we were to optimize our Bunsen, we would get up to about 1200 degrees centigrade. So definitely no hands in the flame here. So this is very much in complete combustion. This is very much complete combustion, or virtual complete combustion of the methane. It's also a homogeneous reaction. It's a reaction between two gas-phase elements, oxygen and methane. And pretty much the same principles apply for combusting coal, except this is more complicated, and now I've got a heterogeneous reaction between a solid and a gas. And the reason why I like this picture that I took out of the web is that you can look at the effects of varying the fuel-oxygen ratio. So here we've got a perfect diffusion flame where the combustion rate is completely dominated by diffusion of oxygen into the flame. And as we introduce more and more oxygen into it, we can see the yellow coloration disappearing. So we can gradually change between this incomplete and this complete combustion. So this is a diffusion flame. This is pretty much a pre-mixed flame. And that's what we're aiming for. Now, if you're in the business of combusting fuels, buying fuels, raising heat to raise steam or something like that, naturally you'd say this is what you want. And this is exactly what you want. So if you're designing an internal combustion engine, you're mixing diesel or fuel with oxygen in a ratio, and what you don't want is lots of particulates coming out. On the other hand, this is much more efficient, it's higher temperature, it's complete combustion. Logically, this is what you would want. And of course, since you want the maximum temperature, you would say that what you want is the correct stoichiometric ratio, the exact amount of air-fuel ratio, so you get complete combustion. In fact, none of this is true. This is where logic starts to break down a little bit, and this is where engineering starts to kick in. So, let me move to the next slide. Just summarize what we've been saying. Incomplete combustion, flame on the left, typical, very complex flame structure. We've got uncombusted gas in the middle, partially combusted gas in the corona, where we've got a correct ratio of oxygen to fuel, so we're getting complete combustion. The flame is also unstable, so it's very difficult to apply any modeling to this kinds of flame unless you've got very well-defined boundary conditions. Combustion is incomplete, and of course we're getting particulates emitted from this. Summarize complete combustion, as exemplified here on the right. What we're doing is we're getting mixing, certainly not perfect mixing, of the fuel and air before combustion, so that oxygen is much less limiting or is completely non-limiting. Most efficient form of combustion, you're getting maximum temperatures. There's not much radiation of energy away from the flame, you can't see it. So of course in our incomplete flame, the yellow, in fact you can see it, means that you're getting energy radiated out of the flame, which again reduces the amount of heat energy you can get out of it. And as I said, the flame temperature is much, much higher. So that's basically these two types of combustion. Which would we choose? Now I'm going to come back to this graph again. And what I'm going to do is to define two types of combustion. And I'm going to be looking at the way in which the flame temperature governs the emission of pollutants from this. So what I've got is a graph here, the fuel-air ratio. I like this graph. So here we have the perfect stoichiometric ratio of fuel to oxygen. And this is what's labeled up here, the ideal combustion. Now, if we have a combustion chamber, and in one side we're introducing air, the other side we're introducing a fuel. It could be anything, it could be vaporized petrol, diesel, gas, practically anything, acetylene. If we put in too much oxygen into the combustion chamber, then the combustion is called fuel lean conditions. And there's a very precise scientific definition of this. So we have our stoichiometry, which we can calculate from the chemical formula of the fuel. We can calculate the ideal amount of oxygen. So that's the stoichiometry. If we push in too much oxygen above the stoichiometry, it's labeled fuel lean combustion conditions. If we don't put enough oxygen in, it's called fuel-rich conditions. Now, clearly, in terms of efficiency, in terms of fuel consumption, if we don't stick enough oxygen in, clearly we're going to get some uncombusted fuel coming out of the combustion chamber. Which is why this graph here, our fuel consumption, you can call it wastage if you want, this tends to increase as we move into fuel-rich conditions. As we push more and more oxygen into it, then of course we've got the conditions for consuming all of our fuel, which is much, much more efficient. So as we move in from our stoichiometry, then we start, of course, we're consuming all of the fuel. But as we push too much oxygen in, then we've got more oxygen coming out, and the oxygen, of course, is hot. So we're carrying heat away from our flame, out of our combustion chamber. Therefore, the efficiency goes down, or our fuel consumption goes up. So there is a sweet spot in the ratio between fuel and air. It varies from fuel to fuel, you can calculate it, where we have the best fuel economy, the most efficient combustion. And you can see this on this graph here. And if you're running any kind of a combustion chamber, be it a gas plant or something like that, a combined cycle plant, a diesel engine, a petrol engine, an aviation turbine engine, if you want maximum fuel consumption, this is where you aim. So this gives you the maximum efficiency out of your engine. And this is calculated, so any engine will be monitoring the fuel-air ratio and optimizing the combustion appropriately. So if you want more power coming out, more fuel goes in, then the air intake will increase, so the whole thing is continuously optimized by means of sensors. So all petrol engines have an oxygen sensor which monitors the amount of oxygen that's coming out of the chamber, and then this feeds back into the control of fuel and air intake by throttling the oxygen or varying the amount of fuel, normally by throttling the amount of oxygen, varying the oxygen intake. So this is where you aim for. It's good for everybody, you save fuel, you're using fuel very efficiently. The times when you need fuel-rich conditions are A, when you're starting up an engine. So if you're starting up a petrol engine or a diesel engine, then stand behind the exhaust, then you'll smell fuel being kicked out there. You'll smell a sort of sweety smell of petrol or diesel coming out there. But that's when you're getting up to optimal temperature, things like that. The other time when you would need it would be for acceleration. So if you've got a high-performance diesel engine or something like that, or a high-performance car, then you'll deliberately operate things under fuel-rich conditions. You're putting enough fuel in there so you're getting maximum power out of the engine. Of course, you're wasting some. So again, if you were to stand behind, well, the classic example is a Formula One car, which basically run on things that look like ether these days. If you stand next to a bend in a Formula One race, as they accelerate out of the bend, they deliberately move over to fuel-rich conditions, which means they're kicking out ether, which will either give you a headache or turn you drunk or something like that. Either way, it's unpleasant, but lots of people pay good money to sniff this stuff. You might just buy a bottle of petroleum ether and release it or something like that. But that's where you would want to operate, under very high performance conditions, when you want the maximum power. But again, Formula One cars these days, I'm no expert, will try for most of the time to maximize fuel. They don't need fuel anymore, so they'll try to optimize that fuel. So logically, this is how you would want to operate. But why not just run at stoichiometric conditions? Two reasons. First of all, the flame temperature is too high, which creates materials problems. And secondly, strangely, it doesn't give you peak efficiency. So there you have it. Logically, you'd want to run this for maximum efficiency, so you're not wasting fuel and producing too much CO2. But when you want to accelerate away from traffic lights, then you kick a lot of fuel in like that. So that is how you would normally want to drive. Correct. Apart from one thing, and that one thing is the emission of pollutants And this is causing all the debate and angst, not just in Volkswagen, I suspect, but everybody else. Now let's think about the production of pollutants. Diesel has very strict regulations on the amount of sulfur it contains. Now, every litre of diesel that you would buy in this country, with one exception being bunker fuel and fuels for aviation, turbine fuels got very, very low sulfur contents. The legislation has been brought up over a number of years, and so sulfur content has been going down. Created problems with lubricants and petrol and diesel and things like that, but that's no longer considered a problem. Sulfur is no longer a problem. The big problem is nitrogen and the production of nitrogen oxides. Now this gives you some fairly complex chemistry, but I've kind of broken it down so you can understand what's going on. Right, so we've got a flame. What do? We've got a high temperature, we've got oxygen there, we've got some partially unburnt fuel, and we might have some nitrogen within the fuel itself. We've got nitrogen everywhere. Now there are three mechanisms by which we can produce nitrogen oxides. The first is called thermal NOx, and this comes from the interaction between the flame and the air surrounding the flame. So in our classic Bunsen burner, very high temperature, over 1,000, then you're getting physical cracking of dinitrogen, nitrogen molecules in the air, and this is giving rise to some interesting chemistry. First worked out by Zeldovich, I can't remember the date, but this is the basic chemistry of the Zeldovich scheme. Three nice, easily understandable reactions. They should be strictly reversible, which gives you all sorts of problems, but I'll try to keep it easy. Now, in these reactions, I'm just considering the formation of nitrogen oxide, NO. In fact, NOx, N-O-X, refers to nitrogen oxides in a series of different oxidation states. So we can have NO, NO2, N2O5, NO2, things like that. So that's a general term. But to keep the chemistry simple, I'm just looking at NO. The big problem is NO2, and there's easy mechanism converting between the two. But for simplicity, I'm just looking at NO. So, this is the initiator reaction in the Zeldovich mechanism. We have nitrogen from the air at a low temperature. Now, in the flame, we're cracking oxygen, so we're producing oxygen-free radicals. Very, very reactive indeed. So these are formed in the flame at high temperatures. So we're having nitrogen from the air interact with oxygen and produces NO plus a nitrogen radical. Again, very, very reactive. The nitrogen radical can react in a number of ways, but in the Zeldovich mechanism, it interacts with molecular oxygen to produce NO plus O. So we've got oxygen back again, so this is kind of an autocatalytic thing. But the oxygen can fall out of this scheme, and it can interact with a hydroxyl radical. Again, this is present in fuel, and it produces NO plus a hydrogen radical like that. The end result of all of these is the production of nitrogen oxide, in this case, NO. Now, this is a thermally induced reaction sequence, which means that as you go to higher and higher temperatures, of course, the reaction rate increases. So, under low temperature fuel combustion conditions, like our yellow flame, this mechanism is virtually insignificant. Very, very low rate. By the time you get to energies enough to break nitrogen and oxygen bonds, then this mechanism kicks in very considerably. And indeed, you can follow the reaction rate as a function of temperature. So, sorry, this is promoted in fuel lean conditions. I apologize for the typo there. This is fuel lean conditions where we've got higher temperatures and the presence of OH radicals from cracking of the fuel itself. So this is thermal NOx produced at high temperature. That's one mechanism. The second mechanism is very much more complicated, and this is given the technical name prompt NOx. Don't know why, but it's called prompt NOx by everybody. Don't know where the name comes from. But this is the interaction of nitrogen with radicals produced from the fuel itself. So if we've got a typical fuel, like, let's say methanol or something like that, or ethanol, or any oxygen-containing compound, you can have an interaction between nitrogen from the air and different radicals from the fuel itself. So for example, in ethane or something like that, the ethane molecule will crack to give a variety of fragments, and one up here is CH. Again, this is a fairly reactive radical, so this can interact with nitrogen to give you HCN, hydrogen cyanide, plus a nitrogen radical, and then the nitrogen radical can react according to the previous Leibovitz reaction pathway. This is a very, very complex set of reactions, because as fuel cracks at high temperatures in the flame, it gives you a whole collection of different radicals. So C, carbon atoms, CH, H, all sorts of things, CH2, CH3. The list can go on, and it varies with the type of fuel. So this is called prompt NOx, essentially a reaction between radicals produced from the cracking of fuel molecules and nitrogen in the air. So we've got thermal NOx, we've got prompt NOx. The third reaction that we have is between nitrogen in the fuel, in the molecular structure of the fuel, and oxygen. So, what I've given you here is the formal definition of fuel lean conditions. If you're combusting a fuel and the concentration of hydroxyl radicals, OH, is roughly the same as the concentration of oxygen radicals, is roughly the same as the concentration of hydrogen atoms, that's called fuel lean conditions. Complete combustion, very, very efficient. Unfortunately, any nitrogen in the fuel reacts as follows. The nitrogen cracks out to give you hydrogen cyanide. All nitrogen has a very complex pathway, but this is the preferred pathway. And now, since we're in fuel lean conditions, it can react with all of these radicals. It can react with oxygen to give you a whole bunch of very strange and unstable compound. This first reaction gives you NCl plus H. Second reaction gives you NH plus Cl. Third reaction gives you Cn plus OH. But the fate of these three radicals is always exactly the same. The NCl from the first reaction interacts with oxygen. Remember, we're fuel, so it's an oxygen radical now, and it gives you NO plus Cl. The NH can interact with an OH from our fuel, remember the conditions, to give you NO plus H2. And finally, the Cn radical can interact with oxygen to give you N and Cl, and then the N subsequently reacts with oxygen to give you NO. In other words, any nitrogen that's present in the fuel itself under fuel lean conditions gives you NO or NO2, or depending on the oxidation state. But the propensity is always for fuel-derived nitrogen to produce NO. So at high temperatures, what you've got is, first of all, thermal NOx because of the flame temperature itself. You've got radicals from the cracking of the fuel interacting with molecular nitrogen to give you NO. And finally, any nitrogen that's present in the fuel, about 1% typically for a diesel fuel, will give you NO. So this highly efficient fuel lean combustion, the outcome of all nitrogen, of all the flame chemistry, is to produce large amounts of NO. Of course, the NO can produce NO2, then you've got an ozone-destroying compound, or you can produce low-level oxygen. So this is why people tend to worry about the production of nitrogen oxide. This is just a little picture. This is actually from coal. I couldn't find a decent one of diesel, just to show you some of the chemical functionalities in fuels that contain nitrogen. You've got some cyclic nitrogen here, some aliphatic nitrogen, some aromatic nitrogen, and there's aliphatic nitrogen in there. So there's a whole library of different nitrogen compounds present, not just in this coal molecule here, but diesels and petrols and things like that. There's always nitrogen present. And in the fuel lean, it always gives you nitrogen oxide. Let's look at fuel-rich conditions. Now, the formal definition of fuel-rich conditions, if you examine the chemical content of the flame, is that you have hydrogen atoms, hydrogen radicals present, and the concentration of hydrogen radicals is much greater than the concentration of hydroxyl radicals, OH, and these are always much, much larger than the concentration of oxygen radicals from the combusting oxygen, of course. So this is the formal definition of fuel-rich conditions, this inequality here. Now the chemistry that takes place, since you don't have so much oxygen and so much hydroxide, is as follows. The nitrogen produces HCN, hydrogen cyanide, which is sadly very weak to listen to the highly toxic gas. But now it either interacts with hydroxyl to produce NH2 plus Cl, or it can interact with, that's basically part of the oxygen molecule, or I can just strip it out and say it interacts with hydrogen to give you ammonia. So just have to look at it this way. You've got NH2 interacting with hydrogen from the fuel, and this gives you NH3. And since the concentration of hydrogen atoms is largest, this is the dominant pathway. So now you've got a reducing atmosphere, and instead of producing nitrogen oxides, you tend to produce ammonia. And then, if you look further in the flame itself, this NH2, for example, can actually reduce any nitrogen oxide that's produced by this reaction pathway. You can have NH2 plus NO, if it is produced, goes to N2H plus OH, and then this gives you benign nitrogen out of the cycle plus H2O. So under fuel-rich conditions, the propensity is to reduce any nitrogen oxide is produced. And in fact, this is the basis of reducing NOx emissions from large thermal plants. Thermal plant operates at very high temperatures, 1300, 1400 degrees centigrade. So you burn most of your fuel under fuel lean conditions, and then you have a small staged burner by which you burn up under fuel-rich conditions, and then you're driving this chemistry, reducing the nitrogen oxides to nitrogen. So this is the path. You tend to produce ammonia, or you can produce nitrogen from it. And indeed, what I'll show shortly is that you can reduce any ammonia by using urea or other chemicals. So that's fuel lean conditions. So let's go back to my little graph here and explain what's going on. Now, normally if you're driving a diesel car, any diesel car, especially modern diesel cars which operate the materials now, give you very, very high compression ratios. Remember that there's compression and the build-up of heat that ignites diesel and diesel engines. Very high compression ratios, very high temperatures, very efficient engines. So this is where you'll operate. You calculate and measure the oxygen concentration in the exhaust. You'll throttle more oxygen in or out to operate under this maximum fuel efficiency. The trouble is, as I pointed out, now you've got very, very high flame temperatures. Admittedly, not as high as the stoichiometry combustion, but you're producing large amounts of NO2. And since everybody wants the latest compression engines and maximum fuel efficiency, and what you certainly don't want is the emission of particulates like soot, this is where you'll drive down the highway, kicking out not clouds, but a significant amount of NO and NO2. Unfortunately, the amount of nitrogen oxide that you're kicking out certainly exceeds very strict regulations in the United States, not quite so strict here. So what dear old Volkswagen have been doing is they've been looking for standard driving tests, and then what they've been doing is they've been kicking more oxygen into the combustion, sorry, more fuel into the combustion chamber, so that under test conditions, the computer's being picked up this driving routine, this driving cycle, and they've been operating under fuel-rich conditions. Don't know tell me exactly where it lies in there, but what they've been doing is kicking off the fuel, reducing the fuel temperature so that it meets the NO2 regulations. So this is what they've been doing. This is why they've been doing it as well. Of course, here lies the dilemma. What do you do? Do you drive around under conditions, fuel-rich conditions, where you're limiting the amount of, I don't know whether it actually goes formally to fuel-rich conditions, but perhaps we might be operating somewhere here. I don't know enough about the test and the exact routines that they use, whether we're kicking more fuel in to reduce the temperature. I suspect it's fuel-rich. So what do? Do you drive around producing large amounts of NO2 as a pollutant, but driving very, very efficiently? Or do you drive around under very inefficient conditions, where the pollutant switches from being large amounts of NO and NO2 to basically CO2, and you're wasting a lot of fuel. And if you're wasting a lot of fuel, then that's going to give you more particulates. Just try driving behind a badly maintained bus in Sheffield or anywhere like that, and you'll get a face full of soot. We've all experienced it, particularly bad in Glasgow, going up hills or something like that, where I said they need a lot of power out, so they're kicking a lot of fuel into the combustion chamber, and the result is particulates. You can't go without buses, so we put up with particulate pollution, which is probably a lot worse than NO2. So getting back on track, what do we do about it? Well, there's nothing easy that we can do about it. If you have a very large combustion chamber, such as a combustion plant, a combined cycle or something like that, then it's stationary. You can add on all sorts of things to eliminate it. I've talked about staged combustion. Most of the combustion is basically fuel lean. Then you have a small combustion chamber where you operate fuel rich and reduce the fuels. There's something called selective catalytic reduction that takes place in all combustion plants to remove NOx. And basically what you do is you have a catalyst bed, typically titanium, vanadium, tungsten. The catalytic is just a honeycomb type of device if you're looking at it. And then you introduce either urea into this or ammonia. So we've seen the fact, I'll just go back and remind you of the chemistry. Here, chemistry here, but NH3 can interact with NO to reduce it back to nitrogen. And similarly here, this is the correct stoichiometry. If we introduce NO, it interacts 4 NO plus 4 NH3 plus oxygen, gives you nitrogen, all of this catalyst plus 6 H2O. So this is the standard method of reducing nitrogen oxides out of a combustion plant. And I've given you the chemistry for N2O reduction as well. Again, ammonia. So what happens in cold combustion plants or combined cycle plants is that you've got this flue gas containing large amounts of nitrogen. They'll pass it over this catalyst here. The temperature's not too bad, 300 or 400 degrees centigrade. They'll monitor the amount of NO in the gas, and they'll inject the corrected ammonia and oxygen, basically to reduce the NO to nitrogen, the most benign compound. So this takes place in a large-scale plant. Could it take place in smaller plants? Well, I'd rather suspect and know that in large trucks and things like that, very large trucks, you can have a font of the rear which contains nitrogen. It's a good reducing agent as well for reducing the amount of NOx. The trouble is, could you do it on small family cars? Currently, it's just too difficult. As soon as you start putting in catalytic beds, extra monitors and things like that, the catalyst can become deactivated. Regulating the temperature is very difficult in small combustion, so when it's heating up it wouldn't be effective. It might become cold or deactivated with carbon, things like that. You're changing the pressures, the flow rates and things like that. So introducing this selective catalytic reduction, I don't think it's feasible. It would add so much to the cost of diesel engines. In my estimation, it would be very, very difficult. It would have to be a major redesign of the whole technology of diesel combustion. But there are solutions to it. So, as I said, I'm not moralizing. I'm just pointing out here, as engineers, there's never a solution. As I said, we all want modern diesel engines that all operate at very high compression ratio. This gives you very high maximum temperatures in diesel combustion. Very efficient, beautiful design, beautiful materials. The trouble is that these enhanced temperatures give you much more thermal NOx, prompt NOx. Well, the nitrogen just goes its sweet way anyway in the fuel conditions. But, as I said, beautifully efficient. So, I come back to my little diagram. Give me scrolling up again. Where do we operate? What do you want? Do you want lots of NOx, or do you want to produce more CO2? As I said, it's a decision, it's an engineering compromise that has to be made. There's no simple way out of this dilemma, except the way that Volkswagen have chosen to approach it is essentially cheating on the tests. Not acknowledging the fact that they're producing large amounts of NO. We all knew that. Everybody knew that. We got through it by cheating, by operating under very inefficient conditions, conditions that you would never want to operate under, just for personal fuel consumption. Well, again, the problem to this takes you, the answer to this perhaps takes you outside of engineering and takes you to the whole area of what is appropriate regulation. Is the legislation too tight on the emission of nitrogen oxides? It says in the compromise between wasting fuel, producing too much CO2, or producing NO. You can't have both, unless you want a much, much more expensive car with these enhanced pollution control systems upon them. But then that would take diesel cars, efficient diesel cars, out of the reach of most people. Public education, well, just look at the headlines. It's quite appalling, some of the headlines that have come out about this. It's a complete lack of understanding of what's taking place here. And I guess it comes down to expectations. What should we expect from personal transport and things like that? And I'm not a moral philosopher, so I'm just posing these questions to you. And I'm going to stop there. So at least I hope you've had a little bit of insight into what is a complex problem. Complex problem not just for engineering, but also from society as well. So that's where I'll shut up. And if you do have any questions, I'll try to answer them. Thank you.